Have you ever wondered what would happen if the biggest force of nature went head-to-head with humanity's most destructive invention? We're talking about a supervolcano versus a nuclear arsenal. It sounds like the plot of a disaster movie, but the reality is far more complex and, frankly, more interesting than fiction. We're constantly bombarded with sensational headlines about both, often blurring the lines between plausible threats and pure fantasy. So today, we're stepping away from the myths and diving deep into the math. We'll separate the Hollywood hype from the hard science to understand the true scale and nature of these two colossal forces. What really happens when you compare the slow, immense power of the Earth to the instantaneous, focused fury of an atomic bomb? Let's find out. First, let's get one thing straight. Am I the only one that didn't know a supervolcano isn't just a bigger volcano? Forget the classic cone-shaped mountain you're picturing. A supervolcano is a geological feature of an entirely different magnitude. It doesn't have a peak. It has a caldera, a massive, sunken crater left behind by a previous eruption of unimaginable scale. Think of it less like a mountain and more like a lid on Earth's weird pressure cooker. Deep beneath the surface, sometimes miles down, lies a colossal reservoir of magma, a molten rock soup simmering with dissolved gases. Over tens of thousands, or even hundreds of thousands of years, this magma chamber slowly fills. The pressure builds, relentlessly pushing up against the Earth's crust. The ground above can swell, rising by inches or even feet per year. Unlike a regular volcano that might blow its top, a supervolcano erupts when the pressure in the magma chamber becomes so immense that it fractures the entire crust above it. The roof of the magma chamber collapses inward, triggering a cataclysmic, sustained eruption that can last for days or even weeks. This isn't a single explosion. It's the catastrophic draining of a subterranean sea of fire. Now, let's turn our attention to the other contender: nuclear weapons. Here, the timescale is flipped on its head. Instead of millennia of buildup, we have destruction in a microsecond. The power of a nuke is measured in kilotons or megatons of TNT equivalent. For context, the bomb dropped on Hiroshima was about 15 kilotons. A single modern strategic warhead can be hundreds of kilotons, or even over a megaton. That's the equivalent of 1 million tons of TNT. When a nuclear weapon detonates, its energy is released in three devastating forms, all at once. First, the blast wave, a wall of compressed air moving faster than the speed of sound, capable of leveling buildings for miles. Second, the thermal pulse, an intense wave of heat hotter than the surface of the sun that can incinerate everything in its line of sight and start massive firestorms. And third, the radiation, an invisible but deadly burst of initial radiation, followed by lingering radioactive fallout that can contaminate land, air, and water for years. The key takeaway here is immediacy. A nuclear detonation is an instantaneous event, delivering its catastrophic payload in a flash. So, here's the real comparison: the core of our myth versus math. Which one is more powerful? The answer depends entirely on how you define power. If you're talking about the total amount of energy released, the supervolcano wins, and it's not even close. A major super eruption, like the last one at Yellowstone, can release energy equivalent to thousands of the largest nuclear bombs ever built. We're talking about an event with a volcanic explosivity index, or VEI, of 8, the highest score possible. But here's the crucial difference: timescale. A single modern nuclear bomb can blast tens of megatons, instantly catastrophic locally. All of its destructive force is unleashed in less than a second. It's a violent, focused, instantaneous shock to the system. Yellowstone's super eruption holds far more total energy, but it releases it over days to weeks. It's not a single bang. It's a continuous, roaring, earth-shattering event. Think of it like this: a nuke is like a sniper's bullet, incredibly powerful and devastating at a single point in time. A supervolcano is like a glacier, Its total force is orders of magnitude greater, but it's applied slowly and relentlessly over a much longer period, grinding everything in its path. This difference in timescale leads to completely different global impacts. Let's start with the supervolcano. The most significant global threat isn't the initial blast, but what comes next. Ash. A super eruption would eject cubic miles of pulverized rock, glass, and gas into the atmosphere, creating a colossal ash column that can reach over 20 miles high, well into the stratosphere. Prevailing winds would carry this ash across continents. Within days, a thick blanket of tephra would cover vast areas, potentially feet deep near the eruption and inches deep thousands of miles away. This would be catastrophic. It would collapse buildings, contaminate water supplies, and grind modern infrastructure to a halt. Air travel would be grounded globally, as volcanic ash can destroy jet engines. Agriculture would face total collapse in affected regions. But the impact doesn't stop there. The fine particles and sulfur gases that reach the stratosphere would form a persistent aerosol layer encircling the globe. This veil would reflect sunlight back into space, causing a phenomenon known as a volcanic winter. Global average temperatures could drop by several degrees for a number of years, leading to shorter growing seasons, widespread crop failures, and famine. In contrast, the concept of a nuclear winter from a large-scale nuclear exchange involves soot from burning cities being lofted into the atmosphere. While the cooling mechanism is similar, blocking sunlight, the source material is different, and the exact climatic consequences are still a subject of intense scientific debate and modeling. So, for the supervolcano, ash, cooling, and worldwide disruption for months to years. With such devastating potential, it's natural to ask, what's the risk? This is where the myth of Yellowstone being overdue for an eruption needs a serious reality check. It's true that major eruptions have occurred roughly every 600,000 to 800,000 years. But volcanoes don't run on a schedule. Saying it's overdue is a statistical fallacy, like flipping a coin and saying heads is due after a few tails. In reality, the United States Geological Survey puts the annual probability of a super eruption at Yellowstone at about 1 in 730,000. To put that in perspective, you have a much higher chance of being struck by lightning. Furthermore, a super eruption wouldn't happen without warning. The kind of magma movement required would generate intense earthquake swarms, significant ground deformation, and changes in gas emissions and thermal activity for weeks, months, or even years beforehand. Yellowstone is one of the most heavily monitored volcanic systems on the planet. We would see it coming. Historically, we have benchmarks for large, climate-altering eruptions. The Toba supereruption 74,000 years ago was a true monster. More recently, the 1815 eruption of Tambora, which was a supereruption but still the largest in recorded history, led to 1816's Year Without a Summer, causing crop failures and famine across the northern hemisphere. So, let's bring it all together. The myth? That a supervolcano is an instant planet killer, a singular explosion that wipes out humanity today. The math? It's a prolonged continent-altering event, whose greatest danger is the long-term climatic and agricultural disruption from ash. Nukes, on the other hand, represent immediate focused devastation on a local and regional scale, with the potential for global consequences in a full-scale exchange. Both are terrifying in their own right, but they are fundamentally different kinds of might. One is the slow, awesome, and impersonal power of planetary geology. The other is the fast, targeted, and terrifying power of human ingenuity turned to destruction. Understanding the science behind these phenomena doesn't make them any less awesome, but it does allow us to replace sensational fear with a more realistic perspective. It empowers us to focus on the real, measurable risks and the scientific monitoring that helps keep us safe. The world is full of powerful forces, both natural and man-made, And the more we learn about them, the better we can navigate our future.